Okay, so thank you. So as you may heard already, this presentation is about mobile mapping accuracy, and we know how important accuracy is for surveyors and our laser scanning professionals. So that's why I want to give that talk about this now. So let me quickly introduce Navis to you. So Navis not only have powerful hardware as the Navis M6 and the Navis VLX, we also have a powerful software suite, what is the Navis IVion Core. And of course, you can have demos of all of it every time, all the time, around the clock in our booth. Or you can also watch the Navis VLX demo, what will be today at 5 p.m. again. So one important thing I need to mention about our Navis VLX is this hook here. So the presentation actually is only about the Navis VLX accuracy, and that's why we need to know that we do have this hook here where we can measure control points with, because later I will show you results using control points and without using control points for global optimization of our point clouds. So let me quickly also show you this slide here where we compare terrestrial laser scanning with mobile mapping systems. So on the left side, you see how you could capture data and do this project of this office building here with terrestrial laser scanners. And you see on the one hand, you need many scan positions, what of course takes time. And you also need bridge scans to register the terrestrial laser scans in the end to one point cloud. When we now take a mobile mapping system, we see that you just walk around the building, you do some loop closures, may capture some control points, and then you're done. What is not only much faster, you also get a higher coverage compared to terrestrial laser scanning, because we not only have these few positions from the terrestrial laser scanner, what means a few perspectives, we also have 1,000 perspectives due to the movement through the rooms, and that's why we have higher coverage in point clouds and less occlusion. So one question we hear from time to time then is actually, if the system is that fast, can it also be accurate? And actually, yes, definitely, and that's what I want to prove to you today. So let's first have a look on the quality of the point cloud. So here you see 3 horizontal slices and also one vertical section of our point clouds. And it's really nice how you can see the sharp edges, all the details. So actually, this is the perfect base for modeling in other software. So you can definitely use our Navis data for doing so. But the next question is, of course, accuracy. Because yes, that looks nice, but is it really accurate? And the problem here is that there's not really an industry standard for mobile mapping accuracy. And that's why we took some other benchmarks from terrestrial laser scanners and total stations to define our own accuracy. And now I will first explain you 3 basic concepts you can use to do so. And afterwards, I will also show you 2 use cases, one indoor use case and one outdoor use case where we capture data with Navis VLX. So let me actually start with this basic concept. What is the concept of sigma 1 and sigma 2? So this looks a little complicated, but actually it's not that complicated, because all you see here is actually a distribution graph. What means that it's actually a function that specifies the probability that a given value lies under this curve in one specific region. And when we now have a look on the specification sheets of terrestrial laser scanning, we usually get a sigma 1 value. That means that the value is represented for 68% of all measurements, what you see here in this darker blue actually. What you can also state, and what we actually do at Navis, is also the sigma 2 values, what ranges from minus sigma to 2 sigma, so the darker blue and also the lighter blue additionally. And those values represent 95% of all values. So in other words, if we state 5 millimeters accuracy for sigma 1. That means that 68% of all measurements have to be inside the range of 5 millimeters, so smaller or up to 5 millimeters actually. Another basic concept I quickly want to discuss here is the relative or local and absolute or global accuracy. So these blue arrows here actually represent a local accuracy, what means that we can measure these points by capturing just from one scan position or just taking a mobile mapping system and not move it, so just put it on a fixed place and just leave it there. These green arrows here represent the global accuracy, and it also means that we cannot measure these points without moving. So either doing several laser scan positions with a TLS or walking around with a mobile mapping system. So actually here you see a possible trajectory. You could walk, do many loop closures in this area to capture this complete environment. And what is also important here to say is that the global accuracy also represents the complete project area. So if we would talk about terrestrial laser scanning, it would mean that the registration area would be included. For mobile mapping, it's also the drift area, or the SLAM area would be included here as well. The third and last basic concept I like to show here is the global cloud-to-cloud comparison. So what we do here is take a reference point cloud, usually captured with a highly accurate terrestrial laser scanner, and then compare our point clouds, the NAVIS point clouds, to this reference data set. We do this computationally and fully automatically so that millions of points can be compared. And here on the left side, you actually see an example. So this is a slice through the point cloud, and most of the area is actually blue, what means we have really small deviations between the terrestrial laser scanner and the mobile mapping system. But here in this area, we also see that something changed there. So there are some deviations inside. So it could be that something moved there, of course, but it also could just be that the mobile mapping system just measured something wrong or had a drift. One other thing we use are these frequency graphs you see here on the right. And there you again see the sigma 1 and sigma 2 values. Just again, this distribution graph. And this is, you will see those again in the use cases as well, because we use those to represent our accuracy actually. So these are actually the two use cases I brought you today. So on the left side, you see an office, also nicely colored with our panoramic images. And on the right side, you see this 20-meter high facade that was captured outdoors, of course. And I will give you some more information about these two projects in a second. So actually, let's start with this mid-sized office. It's actually one big room on the left and then several small rooms also connected with a few more doors and a long corridor. These are more or less 500 square meters, and it took 20 minutes to capture this area. We also captured 6 control points and took panoramic images every 2 meters to get this nice colorization, as you can see here. And then we actually used this global cloud-to-cloud comparison to find out how accurate our point clouds actually are. So as I said already, as ground truth or as reference data, we took a highly accurate terrestrial laser scan here and compared the NAVIS VLX data against those. And what's important to remember here is that for one analysis, for the left one actually, we used we did not use any control points for optimization. But in the right graph, you see optimized data. And when we have a closer look on these values now, you see that without control point optimization, we have 5.1 millimeters for sigma 2 and 12.9 millimeters for sigma 2, and after optimization, we can deliver for 68% of the measurements the accuracy value under 4.5 millimeters, and for 95% of the measurements, we can deliver accuracies of 12.7 millimeters. So what you actually see is that the difference is not really high between these two analyses, and that does not mean that control points are not important, but it means that our SLAM algorithm is that good that in indoor scenarios, it may be possible that a scan without control points is definitely good enough for your deliverables. But still, as I just said, it can be important to still use control points, for example, for alignment of several data sets or for geo-registration. The next example is this nice facade here. So it's 20-meter high, 30 meters width, and we just captured a longer trajectory, actually, of 800 meters outdoors in a street of houses in a really urban area, and then selected just this facade to do our accuracy analysis. And again, we just took a terrestrial laser scan as ground truth for comparison, and yeah, also panoramic images, as you can see. Here again, you also can see a really nice colorization, actually. So you also see these patterns in the stone. Yes, but let's jump into the accuracy. So here again, you see the results of this full cloud-to-cloud comparison. And actually, for this outdoor scenario, we can state that 68% of the measurements are below 5.6 millimeters, and 95% of all measurements are below 12.2 millimeters. What is pretty good, I would say, for an outdoor scenario captured by the Nevis VLX. But let me also show you a bit deeper analysis here, actually. So this nice colorful slide here actually shows the point density. So the reddish and yellow parts have a really high point density, and then with increasing height of the facade, the point density gets less. And we thought maybe our analysis is a bit biased because in the upper parts you have many correct points because everything that is closer to the scanner also has a better accuracy. And then with increasing height, we also have less points, of course, and also maybe higher inaccuracies. So that's what we wanted to analyze here. And that's why we selected these 3 areas of the facade and did the accuracy analysis again. And this is actually the outcome, and actually it's, this was exactly what we expected. So when we have a look on the lower part, so between 1.50 meter and 8 meter height, we see that 68% of the measurements are below 4.8 millimeters, and 95% of all measurements are below 9.7 millimeters, what is better than the overall result for the whole facade. And then, as expected, as I just said, the accuracy values get a bit bigger with increasing height of the facade, up to 7.5 millimeters for sigma 1 in the upper part, and 16.9 millimeters for 95% of all measurements. But still, I would say these are great accuracy for this really high building and for this outdoor scenario, actually. So let me quickly summarize what I just presented to you today. So one big advantage of the Nevis products is that you can scan really fast and have a high coverage, but you still have this high accuracy, what you could see in the 2 use cases. And regarding the control points, maybe now after I showed you these two use cases, you can decide if you really need control points or if maybe also scanning indoors without control points is enough, so you don't have to take a total station with you. Then if CAD or BIM documentation is one of your deliverable, you see that our data are definitely good enough to do so. So we can deliver a level of accuracy, what's also they are called LOA 30, what means 5 to 15 millimeters for sigma 2. And you saw that we can definitely deliver this. I also want to highlight here the power of software. So actually, the SLAM algorithms are really good already, but they will improve in future, and they won't really stop improving. So you buy a hardware now, but you don't buy an accuracy with buying that hardware. It will always get better, and we share our software updates and improvements every few months with our customers so that they can actually expect better mapping devices in the future. And yeah, with all of this, I'm pretty sure that mobile mapping, and especially mobile mapping with Navis products, can change your business to the better and can help you doing more projects much faster, but still having a super high accuracy. Thank you.